All right. Any problems that we haven't done yet from 2008 that people find interesting? Yes?
Question 5.
Question 5. Okay.
I started doing induction. I'm not sure if that's the right thing to do, though.
I mean, it's not a horrible idea to start anything with induction. So d and k are greater than or equal to 2. We want k to the d to be the sum. M goes from 0 to d minus 1. We want the sum. L goes from 0 to k minus 1 of d choose m, L to the m. Okay. So what are people's first thoughts? Bless you.
I did it with D and K both equal to 2.
So 1 is small cases. Good. Other thoughts people had, and I think you'd mentioned induction. What else?
Like change the limits to like looks like binomial.
So do you want to add 1 to the limits? Okay. Change limits. There's something else related to changing the limits.
This is probably not what you're looking for, but there's the identity that 2 to the n equals the sum from k equals 0 to n of n choose k.
Okay. Okay, there's binomial identities. There's something else.
Changing the order.
Changing the order. I will post a video of Cameron waving his magic bubble wand when he was about 2 years old on how to switch the orders of summation.
Did you already give us that?
I probably have already given it to you. I thought I posted
No,
it.
I've seen it too.
Okay.
You did.
Yeah. So when in doubt, switch the orders. It's one of our most common techniques. If you think back to TlQ3, you can change variables and you can switch orders of integration. These are our key ideas. So there's a lot of different things to do here. Small cases is not a bad way to start a problem like this and try to get a feel of what's going on. The fact that we're summing all the way up to k minus 1 and not all the way up to k, maybe we want to complete these sums. And maybe something is being hidden from us. Trying to do it by induction. Now the question is, what would you induct on?
Would you have to do 2 different ones?
So you might have to do a double induction here. Okay? It's more than twice as much fun. It grows more than linearly. Okay? So for a double induction, maybe we fix a k and then induct on d. And if we replace d with d plus 1, oh, we have d plus 1 choose m. So maybe, a double induction and d plus 1 choose m, what does that equal? So d choose m plus d choose m minus 1. This is Pascal's triangle. So maybe if I do a double induction, I can then somehow break things up. I'm going to have to shift my index m a little bit. If m equals 0, what's d choose negative 1? 0. How many ways are there to choose negative 1 people from d people?
None.
None. There's no ways to do it. How many ways are there to choose no people from 5 people? 1. There is one way to do nothing, Seinfeld, okay? Nothing else works. All right, there's the new series that looks like it's the new Seinfeld, but, I'm sorry? Yeah. So here, if you want, try to do this with a double induction. Now what you would have to do is you would also have to induct on k at the same time. So first you do k equals 1, then you would do a generic value of k. So double inductions are possible, but they're not too comfortable. The idea of changing orders is related to binomial identity. We know things, if I have d choose m, L to the m. I'm wondering if I wrote that wrong. Nope. No, that's right. All right, so let's switch orders. So we would have a sum, L goes from 0 to k minus 1, L to the m, a sum, m goes from 0 to d minus 1, d choose m. I claim that this is a really good natural thing to do. What kind of region are we summing over? Positive, I mean, give me this shape. M goes from 0 to d minus 1, L goes from 0 to k minus 1. What kind of region does it look like? It's a rectangle. Whenever you have rectangles, changing orders of integration, changing orders of summation is fine over rectangles. Rectangle interchange is nice. Again, one of the reasons for this class is this is a way to review a lot of the math you've already seen. If I have the integral x goes from 0 to 1, integral y goes from 0 to x, f of xy dy dx. If I want to figure out what I'm integrating over, x goes from 0 to 1, you give me a value of x, y goes from 0 to x. I'm integrating over a triangle like this. So if I give you an integral like this, I'm integrating over this triangle. If I want to switch the orders of integration, I'm now going horizontally. I would now integrate y goes from 0 to 1, integrate x goes from where to where? Y to 1. F of xy dx dy. So you've got to be careful if you have a double integral when you switch the orders. This is one of the most common mistakes people make, is they don't switch the orders correctly. And so you might remember the different bounding curves. You might have called them phi1, phi2, c1, c2, x1 of y, x2 of y, y1 of x, y2 of x, stuff like that. And you've got to be very careful, where am I going from now? This is one of the reasons why we love rectangles so much. Okay? As a last aside, what's one of the most famous changes of variables you can make? Cartesian to polar, to r theta. And so we get x is r cosine theta, y is r sine theta, dx dy is r dr d theta, r is the square root of x squared plus y squared if you want to go backwards, and theta is the tangent inverse of y over x. In Cartesian coordinates, if I was a really good artist, what would I have just drawn? Circle. So it would have been x squared plus y squared less than or equal to 1. And here's my x, here's my y. Here's my r, here's my, well, actually, I think they put theta down here. Not positive. What does a circle look like in polar coordinates? Okay, r goes from 0 to, and where does theta go from? 2 pi. In polar coordinates, a circle is a rectangle. This is one of the reasons why we like doing polar coordinates, is it converts a circle to a nicer set to integrate over. Does that help at all? Okay. So we've now got a much nicer region to integrate over. What does a sphere look like in spherical coordinates? No.
A rectangle.
No.
A sphere.
No.
A cylinder.
You're close. Come on. It's a sphere in spherical coordinates. It's not a cube.
It's a rectangular.
It's a rectangular box. A cube implies all the dimensions are the same, right? We don't quite have that. This is why these coordinates are so useful, is they convert to very nice regions for integration. All right, going back to our problem, we're going to interchange the orders. Yes?
How did you, whenever you changed the order, how did you get that, like you pull out the L to the M?
Well, oh, wait a minute. Oh, sorry, you're right. I can't pull out the L to the M. Thank you. Because L depends on M. Thank you. Yes, you're absolutely correct. I can't pull out the L. Thank you. So now we have an expression like this. Well, if you look at what's going on now, m goes from 0 to d minus 1. We have d choose m, L to the m. This looks very close to something we know. It's very close to the binomial theorem. Okay? The only difference is we don't go all the way up to d. And this then goes back to the suggestion, maybe we should complete things and go all the way up to d and subtract. The other thing is, if you look at it now, we have d choose m, and m is varying. What did we have before? We had d choose m, and we have a sum over L. So this coefficient here, does this have any L dependence? No. We could pull this out, and now we would have a sum of L to the m. L goes from 0 to k minus 1. Well, we actually know that that's going to be a polynomial in k minus 1 of degree m plus 1. And now we have that polynomial. Oh, good Lord. Right? If you really knew you were Bernoulli polynomials, this would be a really hellish way to attack this problem. There are formulas for the sum of mth powers. Right? You don't want to do that. If I take m equals 0, it's easy. If I take m equals 1, oh, then that's going to be k minus 1 times k over 2. You don't want to go that route. This route is much better. If we look at what we have here, what we now have is we have something that looks like the binomial formula. I'm going to write this a little bit more carefully. It's the sum. L goes from 0 to k minus 1. I have a sum. M goes from 0 to d. D choose m. L to the m. 1 to the d minus m. And then I'm going to subtract off the term that I added, the term when I have d. D choose d is 1. So I'm going to just get L to the d. And so I wrote 1 to the d minus 1 to really remind myself that this is looking like the binomial theorem. Okay? What does this sum equal? 1 plus L to the d. So I have a sum. L goes from 0 to k minus 1 of L plus 1 to the d minus L to the d. And I'm summing L goes from 0 to k minus 1. What kind of sum is this? Telescoping sum. This is going to equal 1 to the d minus 0 to the d plus 2 to the d minus 1 to the d plus 3 to the d minus 2 to the d dot 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 plus k minus 1 plus 1 is k to the d minus k minus 1 to the d. Vroom, 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 vroom. Everything cancels, and you're left with k to the d minus 0 to the d. So you're left with k to the d. Okay, so there's the proof. This is a really good green chicken problem. I'm not the originator of this. This is a semi-standard problem. It's getting you to try to look at things the wrong way. Whenever you have a problem like this, if you have multiple ways of attacking a problem, a really good idea is take 3 or 4 different sheets of paper, and on each one, say, I'm going to attack the problem this way, I'm going to attack the problem this way, I'm going to attack the problem this way, and try working with it for a while and see if anything is happening. And if nothing is happening, then go to the different method. How many choices do we have to evaluate this summation? How many ways can we evaluate this double sum? Really, there's 2 ways. Try doing it in the order given. If that's not working, what should you do? Switch it. Try the other. When there's only 2 sums, it's not so bad. If you have double integral, again, switch the orders. The difficulty is when you have to make a change of variables. The change of variables becomes very hard. There's lots of different ways. Some of the problems sometimes give you a trick. They give you a hint as to what change of variables to do. There was one problem we did in Math Puzzle Night this week where they wanted us to find a certain value of t, such that if we integrate from 0 to t, that's the same as integral from t to infinity of a certain function. And they said in part B, actually calculate what the value is given that the integral of e to the negative x squared equals blah. And as soon as they said that, we then knew, oh, okay, we must be able to change variables somehow in part A and have the functions we're integrating become e to the minus x squared. Else, why are they giving us that in part B? So sometimes the problems provide you useful information. I try not to do that, but other people and more compassionate. Okay. Any other problems from the green chicken from 2008? Two. Okay. One of the 5 common log laws state that the logarithm of a quotient is the difference of the logarithms. So when I was in high school, I was never called on in English class, so I actually spent it proving log laws and stuff like that. You should be able to prove the log laws. Log laws are wonderful, they're a lot of fun, but when you start teaching calculus, there are a lot of mistakes that are made. And one of the most common is the log of a quotient is the quotient of the logs. And so here, I'm doing it the log of a difference is the quotient of the logs. So this is 2008, number 2. So this one, I definitely remember creating this. This was inspired by mistakes my students have made over the years. I can't remember if anyone actually made this one, but I did see one student once do the following mistake. I have seen that. Yes. Math would be very different if that were true. All right, so we want to find, so for what b greater than or equal to 2008, does there exist an a such that the log of a minus b is the log of a over the log of b. Okay, when you're doing problems, it's extremely important that you figure out what you are trying to do. What is our goal for this problem? Find which b, yes? So the problem says, for which b does there exist an a such that the log of a minus b equals the log of a over the log of b? Yes? It's not finding the lowest b. It says for which b. Your answer should be the following. For which students in Miller's class will receive a passing grade? There's just one of you that's going to receive a passing grade? Oh, this is so disappointing. I'm sorry? It should be, yes, it should be all of the students in Professor Miller's class will receive a passing grade. My gut instinct is that will happen. For which b? The first thing is interpret the problem. The problem is asking us which values of b greater than or equal to 2008 does there exist in a such that this is true. So your answer should be the set of b is. Know what the problem is asking and answer what's being asked. Okay? Do you need to find for each b which a work?
No.
No. You need to be able to show that there exists at least one a that works, but you don't need to actually list the a. So sometimes we actually have generic proofs. You might use like an intermediate value theorem and say something happens. So over here, it's very important to note that we are not explicitly finding a as a function of b. Could we find a as a function of b? Maybe. Maybe. It's not clear, but and that's definitely one way to attack this problem. Hey, give me a b, let me find the value of a that works. And if I can find for each b a value of a, I'm done. Do you think given a value of b that there will be multiple values of a that work? Probably not. If there's a value where they're equal, if I start increasing a on both sides, I don't think the sides are going to be changing at the same rate. And so my feeling is they probably would not be equal. We could actually take the derivative of both sides as a function of a, and if we show the derivative is positive at that critical value, if the derivative is always positive, there'll be a unique value of a where this works. Okay. So again, in problems like this, if you're having trouble, step one is to be really clear on what you're trying to find. We want the set of such B is ... do not need to find A as a function of B, but that might help. Okay? So any thoughts as to how you would do this? How might we start this?
You could write it out in more ways, so like ln of a minus b, that is also equal to ln of a minus ln of b.
On the left?
It would-
Okay, what do you want to do to the ln of a minus b?
ln of a, the quotient is equal to ln of a minus ln of b. Oh, sorry, never mind.
No.
Is that the
Isn't that, that's ln of a to the ln of, to the negative ln.
oh, not ln, oh, sorry, my bad.
So the log of a product is the sum of the logs.
Sorry, I was,
The log of a quotient is the difference of the logs. Do any of our log laws apply here?
No.
No, we're in uncharted territory, right?
I mean, we could have the right-hand side be equal to ln of a to the 1 over ln of b.
You could try to do something like that, and then say, I'm sorry?
Let's graph something.
So you could graph something. Let's think a little bit about B's. Can anybody give me any weak results about if an A exists, what could you tell me about the A? What possible A's could you have? All right, so which is it? Is it A greater than B or A less than B?
Greater than b, because if a is less than b.
Good. A must be greater than B. If A was less than B, we would have the log of 0 or a negative number. All right? So we know at least A is greater than B. One question is always, again, I haven't thought about this problem in, I think, 6 years. One question is always, how do you want to write a number?
What's ln of 0 again?
Undefined. Negative infinity.
So can we write B
My love of the Yankees.
A times something?
What do we want to do?
We can write B as like A times A.
I would do it the other way around. I would write A as B times something. So you always want to find good coordinate systems, good variables. This is essentially the subject of linear algebra. Linear algebra, if you had to reduce it into one sentence, is what's the most convenient basis? What's the most convenient orientation? What's the most convenient perspective for a problem? Choose the coordinate system that makes things the simplest. Let's write A in terms of B. So let's write A as C times B. That's one way to do it. If we do that, we get the ln of A minus B equals the ln of A over the ln of B. This now becomes the same as the ln of A minus B is the ln of C minus 1 times B equals C, the ln of C plus the ln of B over the ln of B.
You could call ln the ln.
ln is called the ln,
Wow.
natural logarithm. Normally you're supposed to write log. Once you get into advanced mathematics, you write log for base E. Because there were some people who might have been taking the exam who may not have been in an advanced math course, we use the friendly ln to denote natural logarithm. Do you think it makes much of a difference if we change the base?
No.
It should basically be the same. All right, so the question is this a useful way of looking at things?
I mean, it allows you to just get a c over ln of b plus 1.
So we've got a plus 1 over here, we've got a ln of C.
We still have ln of C
But
minus
yeah, you still have, you just have a different number on top.
Right. And so in terms of whether or not this is helping, it's not so clear. Another thing is, we did the problem, I think, where we had the number 100 and we broke it up into 2s and 3s, right? And then we also broke it up into not necessarily integral pieces and saw what was going on. And it came down to trying to plot things. When we look at the ln of A minus B and the ln of A over ln of B, what happens when A is much, much larger than B? Which side wins? So look at extremes. If A is enormous, which side wins? The ln of A minus B or the ln of A over the ln of B?
The left.
Good. Why does the left-hand side win?
Because it's
So if A is enormous, let's say B is 2008 and A is the national debt.
then B becomes negligible.
B becomes negligible. The left-hand side is essentially the natural log of A. Over here, so we have essentially the natural log of the debt here. Over here we have the natural log of the debt divided by the natural log of 2008. What can you tell me about the natural log of 2008? It's greater than 1. It's significantly greater than 1. You know, it's going to be a reasonable number. It's going to decrease this by a nice multiplicative factor. So when A is huge, the left-hand side is the ln of A for all practical purposes. The right-hand side is the ln of A divided by the ln of B. 2008 is at least e to the 4th. So we're going to divide at least by 4. Okay, so if A is big, the ln of A minus B is strictly greater than the ln of A over the ln of B. So we have some information at the extreme. What if we look at the other extreme? What if A is really close to B? What would we have? Which side wins?
The right.
Okay, so the right-hand side. Okay, so why is the right-hand side winning?
Maybe 1.
So this is going to be essentially 1, and this is going to be,
It'll be less than 1.
it'll be very close to 0. So imagine A is B plus 1 over a googolplex. So if A is B plus 1 over googolplex, we essentially have the log of 1 over googolplex. That's going to be a very large negative number. And this will be a little bit larger than 1. Okay, so if A is very close to B, then the ln of A minus B is less than the ln of A over the ln of B.
But if we could think about this like graphing it, it
Uh-huh.
could be possible that the two graphs will always have a point of intersection. So
Hopefully.
Like it
Right.
comes down to finding the points of intersection of two graphs, which might be a much easier way of looking at it than trying to just do the algebra.
You don't even have to find the point. You
Well-
can do non-constructively with like
Well,
intermediate
well, now we can use the intermediate value theorem, right? So if I look at the function, say f of A is the ln of A minus B minus the ln of A over the ln of B. We know if we are around 2008, is the function positive or negative? So the ln of A minus B minus the ln of A over ln of B. Is this going to be positive or negative a little bit beyond 2008?
F of A.
Yeah, if I take a little bit, if I move a little bit over from 2008, negative. So my function is going to be negative in through here. If I go very, very far down, it's going to be positive. Intermediate value theorem, it crosses somewhere. Whether or not there's one cross or multiple crosses, we don't know. You know, it could go up, down, up, down. I find that unlikely, but do we need to care about that for this problem? No. What we've shown is that as long as B is at least 2008, there will be at least one intersection. So which B work? All B greater than or equal to 2008 work. Okay. What properties did we use of 2008 in this problem? None.
Yeah.
It's bigger than 0.
Bigger than 8.
We used it as bigger than e. When we were comparing the two sides over here, we said, well, look, we're dividing by the ln of b. We're making it a little bit small. This is going like the ln of a. So we used the ln of b was strictly greater than 1. So the question is, what if we take b equals e? Do you expect to find a solution? Okay? So if b equals e, we are not expecting a solution. So in problems like this, you sometimes need to use a little bit of information about the year. Okay? I am using the deep fact that 2008 is larger than e. Okay? I could have used that problem this year. I think we could have used this problem in any historical green chicken. Right? There is at least one green chicken where they talk about historical times going back to ancient Greece, I think. And so in one of those green chickens, we might have some problems. What if I chose b to be less than 1? Do you think that there will be a solution?
B so that ln b is less than 1?
Well, let's say I choose b to be 1/2. I've now got a negative number down here. Well, maybe I could have a negative number here if a is just a little bit larger than b. So it might flip it the other way around. So maybe as long as b doesn't equal e, there's a solution. Right? So I only posed the question for b greater than 2008. We see that 2008 is a little bit of a red herring here. Right? That any b greater than e works. I think any b less than e also works. And clearly we don't expect b equals e to work. Right? So my feeling is you should be able to prove that if b is less than e, I think there's also a solution. I've never bothered to do it. Actually, let me check my notes. I do have the solution keys. And so this was problem number 2. Yeah, okay, so I'll go if b is less than 1 over e, then we can write and we can do it. Okay. So again, when you see problems, you want to think about what are the natural generalizations. And you want to really think about what properties do we care about. I think in the Virginia Tech math competition this year, they tried to do something with the year on all the problems, or at least on a large number of the problems. Frequently, you don't care about many things. You might care about the parity of the year. You might care about whether or not the year is a prime. Is the year a perfect power of 2? For a chessboard problem, we're not going to have that for quite a while. Right? What's the next chessboard year? Yes, so we've got a while.
It's not that long. It's really not very long at all.
I mean, the sad thing is if you think about how, the life of a tenured professor, there is actually a non-zero chance I will be writing a green chicken exam in 2048. I'm sorry?
Did you say the sad thing is?
I don't know. We can actually check the video.
I think you said it, yeah.
I might have said sad.
That's so exciting.
You have to take advantage of that. You can start
Right. Oh, I already have half of the 2016 green chicken written.
That's another good one.
I'm sorry?
Next after 2014.
All right. Other questions from the 2008? Other questions? What else did people try and enjoy? We did question 1. So there was a period of time when problems like this enjoyed a huge amount of popularity. X, Y, and Z are positive integers. X factorial plus Y factorial equals Z factorial. Okay? Find all solutions. Okay. The first thing is, can you find any solution? All right, what's the solution?
Zero, zero, zero.
Okay. 0, 0.
Well, we're saying positive.
So we're saying positive integers. 1, 1, 2. Okay. 1, 1, 2. Excellent. 1 factorial plus 1 factorial is 2 factorial. Anything else? Big list. All right.
On the last one, if we'd just written all greater than or equal to 2008, would that be sufficient?
No, not even close. And I mean, depending on our mood, maybe somewhere between 1 point and 5 points. I don't think you'd get more than half credit.
Who grades these?
A committee of distinguished professors. We also have a live video camera to New York where Major League Baseball has a referee review crew that is looking at all the grading live. And there are challenge flags, so if you disagree with the grading, but you only get one challenge per exam.
If you get it right, you get a second challenge.
Yes, yes. If you do get it right, you do get a second challenge. I'm sorry? That is now illegal. You are not allowed to block home plate. The interpretation of that is do not get in the way of people going to food. So there will be healthy food as well as non-healthy food tomorrow. I will talk about this after class. If you have a fan come to the green chicken, I'd love to see this. All right. Anybody have any thoughts about how we should do x factorial plus y factorial equals z factorial? What are your thoughts? Yes.
We could factor out like x factorial.
So one thing is to try to factor. Okay, good. Another one is to order. X less than equal to y less than equal to z. Introduce order. We'll call this the Lord business model of problem solving. Okay? Why is it good to introduce order? Well, I've got some things about x, y, and z. I might as well assume x is the smallest. This is not the same as saying x is strictly less than y.
Can you say x and y are strictly less than z?
Okay? So now, if y equaled z, we would have trouble. So now we can immediately refine this to x less than equal to y strictly less than z.
I think you have maybe you have a straight. No, maybe not.
Well, if x equals z, I'm sorry, if y equals z, the next factorial has to be
I
0.
was wondering if there are any solutions if x equals y.
All right, so let's do that as a special case now. So now we can do this. I'm learning how to walk on the camera. So case x equals y. So now x factorial plus y factorial equals z factorial is the same as 2 times x factorial equals z factorial.
I don't think it's x.
So x can be 1. So we clearly need z to be greater than x. If z equals x, we have a problem. Yes?
Don't we also conclude that x is, or which one's a small one? That y is strictly greater than x?
Well, that's what we're about to from this.
Oh, okay.
But we do have one case when x equals y. So we have need z is greater than x. If z is greater than or equal to 3, it's impossible. Because in that case, you'd have z factorial would be z times z minus 1 factorial, which would be greater than or equal to 3 times x factorial. So we can immediately conclude that z has to be less than or equal to 2. And now we just brute force. Z equals 2, and yes, and that's how we find our solution from before. The 1 factorial plus 1 factorial equals 2 factorial. So again, in problems like this, you can sometimes get partial credit by looking at special cases. The idea is to have a good unified attack on problems like this. And so if we introduce order, all of a sudden now things are a lot easier. We've now got the special case x equals y, and we see, well, the only way that that can hold is z's got to equal 2, because z has to be greater than x, and they're positive integers. So now we can actually go back over here, and we can actually go to 4 now, that x is less than y is less than z. And the hope is that this is now enough information to show that there can't be any solutions. Okay? So if x is 1, y is 2, z is 3, we can just go forward and see that doesn't work. And then you can start looking at all the different cases. There's only infinite many cases to look at. It's count. No, okay. So we don't want to go that route. We want to try to use the fact that we have some separation now between x and y. Okay, so now, so what we want to do now, there you go, is we want to look at the case x less than y less than z. So we have x factorial plus y factorial equals z factorial. Yes?
You could divide by x factorial, and then you're going to get 1 plus, and then some stuff multiplied together for y.
Okay.
And for z.
And for z.
And then you know that y and z share a factor, namely x plus 1.
Okay, you can try to go do a divisibility one. Okay, so you get 1 plus y factorial over x factorial equals z factorial over x factorial. Okay.
Then that's just y minus x factorial.
And then
It's not y minus x factorial. It's y down to,
x plus 1.
okay.
Yes, you do a divisibility argument and say that x plus 1 divides z factorial over x factorial, and that x plus 1.
Okay, wait. Okay, so now what are we going to do?
X plus 1
Okay.
divides the right.
Divides the right-hand side.
Yeah, because z is greater.
So why does x plus 1 divide the right-hand side?
Doesn't divide over x.
Oh, okay.
Comes from z factorial.
And you know that x plus 1 also divides.
Well, I'm not convinced that x plus 1 divides this.
It divides the right-hand side, I don't think it has left.
It does divide.
Because maybe some of the factors from x plus 1 are canceled. Oh, no. Oh, you're just saying it's got to be, okay, you're saying it's got to be z minus 1, ... z minus x plus 1. And one of these, sure. Okay, so x plus 1 divides this side.
But it doesn't divide the whole right, it just divides that piece right.
Well,
That is the whole right.
that is the whole right-hand side.
It doesn't divide the left-hand
Oh,
side.
yeah, that's
Left-hand
fair.
side, yeah.
Okay.
It's the left-hand side that doesn't divide.
Yeah, but it does divide the y part, the y factorial over x factorial part.
Yes.
True.
can't
So-
How does, where do you go from
What
there?
is that?
Because if it divides the entire right-hand side and it divides one part of the left-hand side, then it must divide 1.
Maybe it would be better to go, but okay, so you're going to say x plus 1 divides this, x plus 1 divides this, x plus 1 also divides this.
Yeah.
That works. The other way to do it is to say y divides this, y divides this, y doesn't divide 1. You can do it lots of ways. So x plus 1 divides right-hand side as x plus 1 is a factor. Since z is greater than x, x plus 1 divides y factorial over x factorial as x plus 1 is a factor. Since y is greater than x. And see that we're using both of the givens here. Therefore, x plus 1 divides the difference, i.e. 1. And that tells us that x has to be 0, which can't happen. Therefore, bless you, x equals 0, contradiction. Okay, excellent. So this is a nice divisibility argument. Okay? Any questions on the divisibility argument? Any other ways to do this? You can do this without a divisibility argument. Yes?
You say that x factorial plus y factorial is less than 2y factorial.
Yep.
And then z factorial is less than 2y factorial.
Yep. So we know x is less than y is less than z. X factorial plus y factorial is going to be less than y factorial plus y factorial. This is 2 times y factorial. This is going to be strictly less than y plus 1 times y factorial, if what is true?
Y is greater than or equal
No, actually, let's be willing to do a less than or equal to, because we've already got a strict inequality here, right? So all we need is that y has to be at least 1. Well, since y is a positive integer, this is true. But this is going to be equal to y plus 1 factorial. And because z is greater than y, this is less than or equal to z factorial. And we have one inequality in the chain. Therefore, it can't be true. So there's lots of different ways of looking at these problems. I'm an analyst at heart. I'm not an algebraist. And so for me, I always like to look at how is something growing? How fast is z factorial going to y factorial and x factorial? Well, x is less than y, so x factorial is less than y factorial. The best this could be would be 2y factorial. And it can't even be that. Similarly, the z factorial has to be significantly more than y factorial. And so in terms of just looking at how things go in the limit, okay. So we've now done question 1, question 2, we've done 3. Did we do question 4? No, we didn't do question 4. Consider the following game. We randomly place the numbers 1, 2 through 2008 down on a line. Oh, we did that one in class? Oh, that's the coin problem. Okay, we did 4, but we didn't do 4 recently. We did 4 in the age-old days. Okay. We did question 5. We did question 6. We didn't do question. Did we do question 7? No. Okay. We did question 8. All right. So we did all but one of them. That's not bad. All right. Based on the fact that there's not even 4 minutes left, this is, I think, a good time to stop. So what I will do is I will stay here for a few more minutes in case anybody has any